So last time we talked about localization of R modules. So I will recall a little bit and discuss a few more things about localization, and then move on to define rank and torsion modules and stuff. Okay, so localization of R modules is very similar to localization of rings. You start with R module M and a multiplicative subset S in R, and then you define a relation which happens to be an equivalence relation on S cross M via this formula. So M1 over S1 is sort of equivalent to M2 over S2 when all the obvious things happen. Yeah. So here, even if R is an integral domain, you need this S, yeah, because M could be anything. Yeah? M is not R; it could be any R module. Yeah. So this in this additional S such that S1 M2 minus S2 M1 is 0 in M is very important. So this is an equivalence relation, and the equivalence classes we denoted by M over S. Yeah? And the set of equivalence classes we denoted by S inverse M. Okay. And then on the set of equivalence classes, we define this binary operator plus via this thing, this formula. We show that this is well-defined binary operator on the set of equivalence classes, S inverse M. And then we define the scalar multiples. So it's a function from set of equivalence classes in S inverse R and set of equivalence classes in S inverse M. So set of equivalence classes in S cross R and S cross M, yeah, and the set of equivalence classes is S inverse R and S inverse M, yeah, and then the formula is the obvious formula, and we saw that this is also well defined, and then we saw that this S inverse M becomes an S inverse R module via this scalar multiplication sigma. Yeah. And in particular, S inverse M is an R module because there is a ring homomorphism from R to S inverse R. And then we saw that the natural map from M to S inverse M given by M going to M over 1 is an R linear map. So it's an R module homomorphism. Okay. So and then we computed, we looked at some examples, and as you remember, there was some struggle in working out those examples. So there are some results which sort of help you. So doing particular examples become tedious if you don't know these results. So if you know these results, then it becomes easier. Yeah. So first thing is that S inverse, if you have product of two modules which is same as direct sum of two modules, then taking the localization of the direct sum is same as taking the localization of each of these modules and then taking the direct sum. Yeah. So or direct product. So localization commutes by, with taking direct product. Yeah. Finite direct products. Or finite direct sum. So when you're talking about finite direct product, and then direct sum and direct products are same. Okay. So maybe we'll see a proof of this thing. So we want to give a map from left hand side to right hand side and conversely. Yeah. So we define this map phi. So note phi is well defined map from. Okay, this is too fat. Is a well defined map from S inverse M cross N to S inverse M times S inverse N. Yeah. And So the way we have defined phi m comma n over s to be equal to f of to be m over s comma n over s. So one has to show that this is well defined, because we are sort of in this case. Yeah, so I mean giving so we are using the components. We are using the pieces of the equivalence class. So representative of the equivalence class. Yeah, m comma n and s. So to define this map, so we will have to show that it's well defined. That if we choose another representative, say m1 over n, m1 comma n1 over s1, then we get the same answer. Yeah? So suppose these two are equal in S inverse m cross n, then we want to show that m1 over s1 comma n1 over s1 is same as m over s comma n over s in S inverse m cross S inverse m. Yeah. So what does it mean to say that these two guys are equal in terms of localization? So this means so these two equivalence classes are same, means there exist so they are representative of the same equivalence class, means there exists u in S such that S times the numerator of the first one minus denominator of the first one times the numerator of the second one is 0. Yeah. So u times s m1 over m1 comma n1 minus s1 m comma n is 0 in m cross n. This is what it means to say that these two are same. These two are in the same equivalence class. And then remember the scalar multiplication and addition, subtraction, everything is component wise in m cross n. So what does so you just do the thing for the first component, then you get u s m1 minus s1m in the first component, and in the second component you get u s n1 minus s1n, u times s1n. So you will factor it out, keep it out. And that is 0 in m cross n. What is 0 in m cross n? That is 0 comma 0, where 0 first 0 is m, second 0 is n. So that means that the first component must be 0 in m, and the second component must be 0 in n. Yeah, makes sense. And then this precisely the first component is 0 in m precisely means that m1 over s1 is same as m over s in S inverse m. And second component is 0 in n is precisely n1 over s1 is equal to n over s in S inverse n, because u is in s, remember. Yeah, does this make sense, everyone? So it's a straightforward check, but one has to do a check because we are defining in terms of representative, and hence so we get that the pair m1 over s1 comma n1 over s1 is same as m over s comma n over s in the product. So phi is well defined, and similarly you check that phi is S inverse R linear. Yeah, so this is also not difficult. You just the point is everything is component wise, so you just have to do things component wise. Yeah, so I'll not do this check. Yeah, so this check maybe let me check scalar multiplication. Addition should be similar to should be similar, so I'll just do scalar multiplication check. Yeah, so let's take something in S inverse m cross n. So so mn over s times r over s. So there is a module structure, S inverse r module structure on S inverse m cross n, and we want to show that phi of this is same as we can pull out this guy because S inverse m cross S inverse n is also an S inverse r module, because both S inverse m and S inverse n are S inverse r module. So component wise. Yeah. So this by definition So what is the module structure? You on S inverse. So what is the module structure of S inverse R on S inverse M? You multiply the numerator with the numerator and denominator with the denominator. That was the definition. Yeah, R over S times M over S prime is Rm over S times S prime. So we'll do that. So this is phi of Rm times n is same as Rm comma Rn. That is how component-wise multiplication happens, and denominator we get. So maybe I should take S prime here for R over S prime in S inverse R and Mn over S in S inverse M cross N. And this is same as, so I'm doing this check here. Yeah, so and this by definition of phi is Rm over S prime S comma Rn over S prime S. Yeah, and now this is of course R over S. So R over S prime dot M over S comma N over S is so this the scalar multiplication on S inverse M is just component wise. So you'll get Rm over S S prime, and similarly on N, and then this is component wise. So this is how this is same as this thing. The first these two terms are equal, and then this is same as R over S prime, and M over S comma N over S is precisely phi of Mn over S. Yeah. So phi is stable under scalar multiplication, and you can also check under addition. So it's not difficult. It's probably easier. Okay. So so that is so that shows that phi is S inverse R linear, and then we have to also show that it's injective and surjective. So instead, I'll give you a inverse map, yeah, and prove that this is inverse, yeah. So we want to give an inverse map from S inverse M cross S inverse N to S inverse M cross N. So we'll have to send. So our typical element in S inverse M cross S inverse N looks like M over S, comma N over S prime. For M in M, S in S, and N in N, and S prime in S. Yeah. So what should this element go to? Any guesses? In S inverse M cross N.
So MS prime comma NS by SS prime.
Yeah. So you can. So usually we write action on the left. So S prime M comma Sn over SS prime. The point is M over S is same as S prime M over S prime S. Yeah, and N over S prime is same as Sn over S prime. Yeah. So and once the denominators are same, you know what to do. Yeah. So to make the denominator same, we multiply both numerator and denominator with the respect appropriate. So you take C to be this map. So again, one has to check that C is well defined, and because you see we are again using the components. Yeah. So check C is well defined, and the inverses too. So maybe this check inverses will check C is well defined. Check this computer. Okay. So so let's try this. So again, we will check that one has to check that C is well defined. So that I'll leave it for you to check. is similar to what we did here, and then we will check that phi and c are inverses to each other. Yeah, so some checks we will do. So so why are phi and c inverses to each other? So you first apply phi to mn over s, and then apply c. Then this is c of m over s comma n over s, because that is the formula for phi of mn over s. And the formula for c is that you just multiply the two denominators, so you get s square here, s prime over so no, not s prime, but sm comma sn. Yeah. But we can see that this is equal to m comma n over s. Yeah, because of the so these two represent the same equivalence class, because you have this s factor out. Yeah. So this shows that C composed phi is identity, and similarly phi composed C of m over s comma n over s prime is phi of s prime m comma s n over the s prime s or s prime, it doesn't matter, we are in a commutative ring. Something flashy. Okay, and this is same as this is a pair, yeah, and then this is same as we just apply the formula for phi. So first factor over the denominator, so s prime over m comma s prime over s comma s n over s prime. Yeah. But this, of course, again is same as m over s. So in S inverse m cross S inverse n, this is same as m over s comma. So this implies the other way is also C composed phi is also identity. Yeah. So so that tells you that phi is also bijective. Yeah. Hence we get this isomorphism. Yeah, so that proves that the two rings S inverse m cross n and S inverse m cross S inverse n are isomorphic. Any questions?
So is there any sort of universal property for this localization?
Yeah, so there is a universal property as well. So maybe I'll tell you. Let me prove one more property, and then we will I'll tell you something about the universal. So I'll have to write it down somehow. So yeah, so after this one, maybe I'll tell you what the universal property of localization is. Okay.
Okay, thank you.
So these two properties. So this one we used in the last class for writing the localization of z plus z mod 15, z cross z mod 15 by a certain multiplicative set. So you just have to do them separately. No? Now, how do you deal with z mod 15? So we sort of struggle there. So here is a formula. So say R is a ring and S is a multiplicative set, like in the previous example. And I in R is an ideal. Then and say M is the R module, R mod I. Yeah. So R mod I is an R module. Then S inverse M is you can show is same as S inverse R mod S inverse I. Yeah. As S inverse R module. So recall what is S inverse I? S inverse I, remember, is same as I S inverse R. So ideal generated by the image of I in S inverse R. Yeah. So we saw that this is or as a set, this is basically X over S, X in I and S in S. Yeah. So this is as a set, this is the description, and you show that this is closed under addition and multiplication. Okay. So then in particular, if you know that I intersection S is non-empty, then S inverse I will become the whole thing. Yeah, because if I intersection S is non-empty, then that tells you that some element of S inverse I will be a unit. Yeah. So say it contains an element little s, then S over 1 will be in little s, and so S over S will be in S inverse I, but S over S is same as 1 over 1, which is the unit in S inverse R. Yeah, so S inverse I will be the whole ring, and this quotient will be the 0 quotient. Yeah, so that will tell you that S inverse M is 0. And so as soon as you take S such that I intersection S is non-empty, then you get that this is 0. So from there, so once you know this result, then you know that if you invert 3 in Z mod 3, then of course if you invert 3 and try to localize the module Z mod 3, then you'll get 0. Yeah, because the ideal 3Z contains 3, and the multiplicative set also S also contains 3. Okay, even if you try to, so if S is 1, 3, 3 square, etc., and M is Z mod 9Z or 81Z, something like that, then also it's is 0, because 81 is in S. Yeah, so 81 will become a unit is in both I and S. Yeah, so 81 will become a unit, and what you'll get is 0. Okay. But remember, 15 is not in S. Yeah, so whole of 15Z will not become. So if Z mod 15Z, you split it as Z mod 3Z plus Z mod 5Z. Then Z mod 3Z part becomes 0, and what remains is Z mod 15Z, Z mod 5Z. Okay. So S inverse of Z mod 5Z, and then you can check that that is again Z mod 5Z. So in fact, we will prove something slightly more general than this. So if N is a submodule of an R module M, then what you can show is S inverse M mod N is isomorphic to S inverse M mod S inverse N. Yeah. So this is a special, the previous statement will be a special case of this, because we call that S inverse I. I is a ideal of R, means I is a submodule of R viewed as an R module, and then S inverse I is same as S inverse I as an R module, and then you get this. This when you take M to be R and N to be I. Yeah. So this again is something which we can use to compute the localization. Okay. So there are various things in this statement. First of all, this also tells us that S inverse N is a submodule of S inverse N. And so one has to check that as well, that S inverse N is a submodule of S inverse N. And then one has to show that these two modules are isomorphic. Okay, so we will use the first isomorphism theorem. Yeah, so what we'll do is give a map from S inverse M to S inverse M mod N, and show that the kernel of phi is S inverse, is going to be isomorphic to S inverse N. Yeah. and that will prove that S inverse M mod S inverse N is so S inverse N is a so remember, what is the description of S inverse N? S inverse N consists of equivalence classes of some subsets of S cross N, and S inverse M is equivalence classes of some subset of S inverse S cross M. Yeah. So somehow you can't say that these two equivalence classes are going to be same. Yeah. So you'll have to give a map, a natural map from S inverse N to S inverse M, and show that that map is injective, and then and are linear, S inverse are linear, and hence you'll get a natural submodule. Yeah. The image is going to be naturally a submodule. So everything, it looks tautological, but one has to keep in mind that there are different things. Huh? So one has to be careful. Okay, so what you do is define this map phi from S inverse M to S inverse M mod N by this natural map. So M over S, you send it to M bar over S, where M bar is the image of the quotient map from M to M mod N. Yeah. So M bar is M plus capital M. Yeah. Give me a second. Okay. So this is the map. So first thing one has to check is that phi is well defined, because you know, we are defining it in terms of, again, the representatives, not in terms of M over S itself. So say M over S is same as M prime over S prime. So what does that mean? So there exists U in S such that U times S prime over times M minus S M prime is 0 in M. So this is the 0 of the module M. So this implies, so now you apply the quotient map Q from M to M mod N, then it basically puts bar on the elements of M, and remember Q is R linear. So if you apply Q, you will get U times S prime Q M, which is M bar, minus S times Q M prime, which is M prime bar, is going to be 0 in M mod N. So now this identity is in M mod N. Yeah, so you get this, but this precisely means that M bar over S is same as M prime bar over S so now this happens in S inverse of M mod N. Yeah, so phi is well defined, and again one has to check that phi is S inverse R linear, and so that means you have to check that it's closed under addition and scalar multiplication, or you can do it in one go. And again, this again follows from the fact that Q is basically R linear. So if you take M over S and M prime over S prime and apply phi, then and so add them and apply phi is same as first applying phi and then adding them. Yeah, so there's nothing much in there. Yeah? So you just check this. This is one step check. Yeah. And this is also surjective by definition, because if you have something in S inverse M mod N, then it typically looks like M bar over S for some M in M. Yeah, and its preimage is precisely M over S. Yeah, so surjectivity is also immediate. So now we just compute the kernel. Yeah. So kernel of phi is so we have to take all equivalence classes M over S such that its image is 0 in S inverse M mod N. So that is same as saying M over S such that M bar over S is 0 over 1 in S inverse M mod N. So this is M over S such that what does it means to say M bar over S is 0 over 1 in S inverse M mod N? saying that there exists U in S such that U times 1 times m bar minus S times 0 is 0 in m mod n, the module you are localizing. But S times 0 is 0, so we can forget about it, and 1 times m bar is just m bar. So what it says is that is U times m bar is 0 in m mod n, where U is some element of S. So remember, m mod n is also an R module, so U times m bar makes sense. And what does it mean to say U times m bar is 0 in m mod n? That precisely means that U times m bar is just um bar. Yeah, that is how the R module structure is given. So U times m bar is um bar. So um bar is 0 in m mod n means um, the element U times m of m actually lies in the submodule n. Yeah. So it's m over S such that there exists U in S such with um belonging to n. So this is the description of kernel phi. Yeah. Now we want to show that kernel phi is going to be isomorphic to S inverse n in some natural way. So S inverse n, there is a natural map from S inverse n to S inverse m, which we denote by I, which sends n over S. So here n over S is the equivalence class in S cross n. Yeah. So here this n over S denotes the equivalence class in S cross n. This n over S in here, and this n over S is equivalence class in S cross m. Yeah. So they have the same notation, but they are equivalence classes in different sets. Yeah. So technically they are different. So if you think of it as which subset of S cross n you are looking at, that's going to be different from which subset of S cross m you are looking at. Yeah, maybe different if n and m are different. Okay, so there is so what I'm trying to say is there is some something in there. Yeah, it's not I'm not being facetious. Yeah, there is something. These two are different elements, and this lies in this set, and this lies in this set. So there is something to check. Yeah, but it's all tautology, so it's not difficult to check. But they are not the same thing. That's what I'm trying to say. So there is no natural way of putting this as a subset of S inverse n. So there is no natural way of putting S. So you can't think of S cross n mod this equivalence relation as subset of S cross m mod equivalence. You can give an injective map, and that is what we are doing. Okay, so the claim is that this map is injective S inverse R linear with image kernel image same as kernel phi. Okay, so once if we prove this claim, then of course the claim will imply that S inverse n is an S inverse R submodule of S inverse m. If we identify S inverse n by the image of I, yeah, and by first isomorphism theorem, we'll get this this isomorphism. S inverse m mod S inverse n is S inverse m mod. Okay, so all it remains is to prove this claim. And then we are done. Yeah, so let me just prove this claim here. So we want to show that I is injective, and we want to show that is S inverse R linear, and its image is same as kernel phi. Yeah. So let's say, so as I said, this is sort of tautology. So we want to say I is injective. So so what does it mean to say? So I have to also check. Yeah. So first I should check I is R linear. Yeah. uh, is S inverse R linear, in fact. Both are R module as well. So R linear or S inverse R linear, whatever you like, you can check. So maybe, since I've written R linear, let's just check first I is R linear, and then to check its injective, you only have to check that if something is the image of something is 0, then that element is 0. Yeah. So one should. So this check for injectivity works only if it is a group homomorphism at the very least. Yeah. So it is going to be a group homomorphism because the group the addition and scalar multiplication is actually R linear map is defined in the same way in both S inverse N and S inverse M, and this the map is in symbols it's a identity map. Yeah. So if N over S plus N prime over S prime, I of this is just S prime N plus I of S prime N plus S N prime over S S prime. And the formula for I is you just take the same numerator and denominator, and you have to also check it's well defined. So well defined also, is some identity involving elements of N and S. So of course it is well defined. So I is so first one has to check these things, yeah, and then the remaining part. I is well defined, and then this is same as S prime N plus S N prime over S S prime, but that is same as N over S plus N prime over S prime. Yeah. So it is a tautology, yeah, and well defined is also a tautology. Okay. And then you check that it is injective. So injective means that if N over S is 0 over 1 in S inverse M, then you want to show that N over S is 0 over 1 in S inverse N as well. Yeah. So N over S is 0 over 1 in S inverse M means there exists U in S such that U times N minus S over 0, S times 0 is going to be 0 in M, but which is same as saying U times N is 0 in M. Are you guys still with me? Yeah.
Yes, sir.
Okay. So U times N is 0 in M implies U times N is 0 in N as well, because M and N has the same 0. N is a submodule of M. So N over S and U times N is 0 in N. N precisely means that N over S for any S in S, in fact, is 0 is 0 over 1 in S inverse N. Hence I is injective. Yeah. So maybe I should mention this, that first check this, yeah, and then check this part. Okay. So so that tells you that I is injective, and finally we want to show that the kernel of phi is same as the image of I. And we'll use the same notation for the image of I as so S inverse N is the notation we'll use for image of I. So for N in N and S in S, let N over S belongs to kernel of phi. Then so for N in N and S in S, N over S obviously belongs to kernel of phi, right? Because what is the description of kernel of phi? Is M over S, where M is an element of S, and such that U times M belongs to N for some U in S. So you can take U to be 1, yeah? So take, make it slightly faster. So take U to be 1 here, yeah, to conclude that N over S is in kernel of phi. So that means that S inverse N, which is we identify as image of S inverse N under I, is contained in kernel of phi. Yeah. Now conversely, we have to show that if we take something in kernel of phi, then it is of the form N over S for some N in N and S in S. Yeah. So let M over S be such that U times M belongs to N for some U in S. That is what an element of kernel phi looks like. Yeah, so that tells you that M over S is same as but U times M is in N. So M need not be N, but U times M is in N. But M over S is same as U times M over U times S. Yeah. So and that belongs to S inverse N. Hence, we get that kernel of phi is same as S inverse N. Okay. So we have both inclusion and hence this identity. So that completes the proof of this other lemma. Yeah, that S inverse M over N is isomorphic to S inverse M over S inverse M. So what we have also shown is that so we have shown something slightly more. Yeah, so we have shown that S inverse N is a submodule. I mean, so in this small equation, this information is embedded that S inverse N is a submodule of S inverse N. In fact, slightly more general is true. So if phi is a linear map from N to M, where N and M are R modules, so phi is an R module homomorphism, then you can define a map from S inverse M to S inverse M as an R, which will be an R module homomorphism. So the natural map N over S going to phi N over S is a S inverse R module homomorphism. Okay, so this maybe I'll put it as an exercise, or maybe a homework. I'll think about it. So maybe, I mean, the proof is similar to what we did. So there is a basic check. So maybe exercise, not homework. Okay, no trickery here. Okay, so this is the natural map. So you can show that if phi is injective, S inverse phi is injective. And if phi is surjective, then S inverse phi is surjective. Okay, so this really behaves well with the localization really behaves well with respect to morphism. Injective morphism goes to injective morphism, and surjective morphism goes to surjective morphism. Okay. Any questions? Okay. So so maybe we'll take a break, and then maybe I want to talk about rank next. So that universal property I'll leave it towards the end, depending upon time. Yeah, and talk about rank and stuff after the break. So let's take a 6 minutes break. So maybe yeah, maybe let's take a 5 minutes break. So maybe around 12:02 or 12:03 we'll meet.
Excuse me, sir.
Yes.
So could you please scroll down a bit?
Yeah, I'll scroll. Yeah, this part you want to see, yeah?
Yes, sir.
Yeah.
Thank you, sir.
You're welcome. Recording. Okay, so that was about localization. So I'll maybe come to the universal property a little later. Let me just finish this rank business. So this was the reason for defining rank, because it's slightly easier to think of rank in terms of localization. There are other definitions, but one of them will be in the homework. But this is slightly easier to visualize. Yeah. So what is the rank of an R module for R and integral domain? Yeah. So I will only work with the rank of a module over integral domain, and not general. Yeah. So maybe so there is another definition which is slightly more general, and that sort of works out. So for integral domain, they happen to be same. Yeah. So what is it? So let R be an integral domain and M be an R module. Then rank of M is dimension of S. So remember, S inverse M is a S inverse R module. So it's dimension of S inverse M as an S inverse R module. So where S is R minus 0. Yeah. So if you take S to be R minus 0, S inverse R happens to be the fraction field of R, right? So this dimension makes sense as vector space. Yeah. So this S inverse R is a field. Yeah. So back R. So I guess I've already written it's the field. S inverse R equals K is a field. So maybe I'll just put VS here to say it's a vector space dimension. Okay, so this is what rank of M is. So if R were a field, its rank is same as the dimension, but since R is not a field, R may be a general module, then rank is same as the vector space dimension of this thing. So for instance, let's consider this ring. R is Z and M is this module. Then what is rank of M? What will be the rank of M in this case? So you'll have to invert everything but 0. Yeah. So invert all non-zero integers and compute S inverse M. So what will be? So what is S inverse M? Rank will be 3. Okay. So let's just check. So well, S is R minus 0. Huh? So we learned that S behaves well with direct sum. So of course this is going to be so this one should think Z square means Z plus Z. So this is S inverse Z plus S inverse Z plus S inverse Q plus S inverse Z mod 15 S inverse Z plus S inverse Z mod 9 S inverse Z. Yeah, by the results which we know, yeah, which we just proved. So S inverse Z is same as Q, right? Because S is actually R minus R is C, so yeah, so it's okay. So S is all non-zero integers. So S inverse Z is Q. So you have 2 copies of Q. What is S inverse Q? So Q is already, I mean, you have already inverted everything in Z. Yeah. So S inverse Q is again going to be Q. Yeah. So so this is another fact which maybe one has to prove, but this is also going to be Q. And these 2 terms is going to be 0 because 15 does intersect S. Yeah. So 15 is non-zero. Yeah. And so is 9. So this is just Q3. So the only thing here we are using is that S inverse Q is equal to Q. Yeah, is isomorphic to Q as Q vector spaces. Okay, so this you can just check. So what will be the map? So Q is already a fraction R over, so maybe let's call it alpha over S, where alpha is some rational number, then this goes to 1 over S alpha. Yeah, so that's also a rational number. So this is the map, and you can check that that this is an this is an isomorphism of Q vector spaces. Point is alpha over S. So alpha is some, so the point is if you take alpha to be some rational number R over M over N, M over N, and divide it by S, this the class of this and the class of M over NS is same. Yeah, so you can just verify that these two have the same class. In S inverse, this is same in S inverse Q. Okay, and hence you will get that this map is not just S inverse R linear. It's not only Q linear, but it's also bijective. Okay, so a lot of things get clubbed together here. Okay. So that is, what about if I take, consider the ideal generated by, so if I consider R is Z and M is 2Z. 2Z is an ideal in R, yeah? So what is rank of M?
So it will be 1.
It's again 1 because S inverse M is again, you can show is isomorphic to Q. Okay, so it's S inverse 2Z, but you can show it's isomorphic to Q. Okay, so the rank M is again 1. In fact, if I is so what you can generally show is if I contained in R is non-zero proper ideal. No, proper is not necessary. Non-zero ideal of an integral domain R. Anyway, we have defined rank only for integral domain. Then rank of I is 1. Okay, basically you get you are inverting something, yeah. So S inverse I becomes same as S inverse R because something gets inverted. Some element of I, non-zero element of I becomes invertible. So S inverse I is S inverse R. That's the argument we used here as well. Yeah? So so you get it is one-dimensional as S inverse R vector space or K vector space, right? K is the fraction field. Okay, any questions? Okay, so so next I want to talk about torsion, but maybe let's just discuss about this universal property of localization since we are here, and then maybe if time permits I'll talk about localization. Okay, so maybe we'll discuss it here. Universal property of localization for modules. Let's see if we can make a statement here. Okay. Universal property of localization. So yeah, so what do we have? So M and R module and S contained in R multiplicative subset. Then we get an object S inverse M. We also have a map, a natural map phi. Let's call that phi from M to S inverse M. Phi is R linear. And S inverse M is a S inverse R module. And let's see if we can cook up some universal property for S inverse M. Yeah. So say, yeah, so let N be a, so we want to cook up some universal property for S inverse M. So S inverse M is some S inverse R module. So let N be an S inverse R module. Yeah, so it automatically has an R module structure. Then N has an R module structure. Yeah, by R dot N equals R over 1 dot N. Yeah, via this guy. Let theta be a map from S inverse M. No, S inverse M is the guy whose universal property we want to prove. So theta be a map from M to N, which is so M is just an R module. So all you can assume is that theta, which is R linear. Then the claim is there exists and hopefully unique theta tilde S inverse R linear map theta tilde from S inverse M to N such that this diagram will commute. Yeah, so first you apply phi and then apply theta tilde and you get theta. Okay, so this will be the universal property of localization. So maybe in picture M S inverse M, and you have a map to N, which is an S inverse N module. So you start with the assumption that N is an S inverse N module, and hence it's an R module, S inverse R module, and hence it's an R module as well. And theta is an R linear map. Then you get a map from this S inverse. So then you can sort of fill in this dot this way. So you can get a map from S inverse M to N theta tilde such that this diagram commutes. So this is the natural map. Yeah. So maybe let's just see a quick proof of this thing. So we just have to cook up theta tilde and the rest of the check will be easy. Yeah. So proof. So what is theta tilde? So there are many things given. So we only have to check theta tilde exists and is unique and is S inverse R linear. So theta tilde of M over S, what do we define? So of course we know what theta of M is, some element of N, and then what can we do with S? So you just send. So remember N is an R S inverse R module. So 1 over S times theta over M makes sense. Yeah. Theta over M makes sense. So define, and this is well defined. So we are defining in sort of breaking it up. So is well defined. S inverse R linear map. So this is the claim. Okay, and then one has to prove uniqueness as well. So let me so well-defined part should be straightforward. So and then yeah, so everything should be straightforward. So let me just check well-defined. So M over S equals M prime over S prime in S inverse M implies there exists U such that U in S, that is such that U times S prime M minus S M prime is 0 in S inverse M, in not S inverse M but in M. This identity holds in M. So this implies you apply theta to it and still it is 0. So theta of U S prime M minus S M prime is 0 in n now, because theta is R linear. This tells you that this is same as u times s prime theta m minus s theta m prime is 0 in n, and this precisely means that yeah, so this means that theta m over so this means that s prime theta m. So s, remember, is a unit in n, because I mean s acts as a unit. S is a s inverse R module as well. Yeah. So and u is unit in s inverse R. So if this product is 0, that tells you that s prime minus s theta m prime is 0 in n as u unit in s inverse R. Yeah, so you can just multiply by 1 over u if you like, and still it remains 0 in n, which implies and then you multiply by s 1 over s times s inverse s prime. Yeah, so this implies that theta m times 1 over s is equal to 1 over s prime theta times m prime. So you multiply by 1 over s prime. Here you are multiplying by 1 over u. Okay, because all these things are unit in s inverse R. So you get this theta tilde is well defined, and theta tilde of m over s plus r times m prime over. So you have to check this is R linear as well. So maybe I'll do it somewhat differently. So you check that m1 over s1 r over s m2 over s2 theta tilde of this is same as theta tilde of m1 over s1. So I'll just write what you have to check. Theta tilde of m2 over s2. Okay, so you just verify this. So this should be this will be routine. You just use the formula, okay, and see that both left hand side and right hand side are same. Okay, makes sense, everyone? Okay, I hope you guys are still with me.
Yes.
Okay, so and then check uniqueness, yeah. So how do you check uniqueness? You know, if I don't know, alpha is another map. Alpha is another map from S inverse M to N, which is such that alpha composed phi is equal to theta. Then show alpha is equal to theta tilde. Yeah, so it will take same element. So the way things are so on particular values it's going to be same. Yeah, because alpha composed phi has to be theta. Yeah, so for instance, if you take m over 1, then it has to alpha of m over 1 will go to theta is basically theta m. So alpha of m is going to be same as alpha of m over 1 is going to be same as theta tilde of m over 1, and then you use linearity to check that is going to be identity on all of them. Okay, so this is also sort of straightforward. Yes, I'll leave this for you to check. Okay. Any questions? So this is the universal property of localization. Okay. So there is there is torsion as well. So maybe I'll just define torsion, and which maybe you have seen in. I think there was some homework problem related to it. So you may have seen it, but it's. So next time I'll recall it, and we don't need much about it, but we need to know what torsion modules are. Yeah? So definition. So we are going towards proving this. So we are going towards proving this theorem, structure theorem of finitely generated modules over PID. Yeah. So I'm trying to develop whatever ingredients are there for that. So let R be a ring, and M be an R module. Then Tm, the set Tm, called the torsion elements of M in M, such that there exists R in R, R not equal to 0, Rm, but Rm equals 0. So such elements are called torsion elements of M. Okay. So I think maybe this was a homework problem, that Tm is a submodule of M if R is an integral domain. Was this a homework problem?
Yes, sir.
Yes, sir.
Yes. Okay. So we are already done with this, right? But in general, this need not be a. So was that also a homework problem, that if R is not an integral domain, then this need not be a submodule?
Yes, sir.
Okay, good. So we are already there. So Tm is a torsion module of M, and what happens is that so let R be an integral domain. So first of all, some definition. Sorry. M is called torsion free. R module if Tm, the torsion part of M, is 0. Yeah, so 0 has to be there, but there is nothing more. Yeah. So so the first observation is let R be an integral domain M an R module, then M mod Tm. So Tm is a submodule now because we are over an integral domain. Yeah, is torsion free. Okay. So this is not. I mean, this is straightforward. So you have removed the torsion part. So what remains is indeed torsion free. So you have to just check that if R times yeah. So maybe okay, sort of a proof. If R times M bar is 0 in M mod Tm, then we want to say that M bar is already in Tm. Yeah, this implies Rm bar is 0 in M mod Tm, which implies Rm is in Tm, torsion part of M, which implies there exists are not equal to 0. Yeah, so that I mean I'm trying to show that m bar has to be then 0. Yeah, so there exists r prime in R. So it is in Tm means there exists r prime in R prime not equal to 0, such that r prime Rm is 0. Yeah, this is what torsion definition of torsion elements mean. So this implies m must be in Tm. Yeah, since r prime times r is not equal to 0, as r is our integral domain. Okay, so product of two non-zero elements is non-zero, which implies m bar is 0. Yeah. So if you have a ring and if you take a module, you go mod the torsion part, then what you get is something which is torsion. And so last statement, and this is where we will end. And I won't prove it. You can check for yourself. Are an integral domain. M and R module such that M equals Tm. So this means there is a term for it. That means that M is torsion module. Then rank of M is 0. Okay. So if you invert everything, then what you get is the 0 module. Okay. Okay, so this is where we'll end, and maybe I'll sketch down a proof of it next time. If you don't figure it out.
Sir?
Yes?
Sir, is the recent homework to be submitted today or next Tuesday? There is a confusion.
Which homework? The
recent one which you, like one question was on annihilation.
What does the Moodle say?
Moodle says next Tuesday.
Oh, okay. So maybe I by accident I may have given more time, yeah. But it's okay. You can take your time. But it's beneficial if you turn it in quicker. So I'll assign this homework as well, and maybe I'll put it the due date to a few days after 1st of December. Okay.
So it's next Tuesday, right?
Yeah, next Tuesday you can submit it. So it's all machine done. So I don't have much control over it anyway. Okay.
Okay, thank you, sir.
You're welcome. Any other question? Okay, so if there are no questions, let's stop.